Dear students, in this video we will discuss the two-dimensional crystal defects. Two-dimensional defects or surface defects can be divided into the external surfaces, grain boundaries, and stacking fault. Grain boundaries can further be divided into the tilt boundaries and twin boundaries. First of all, we will discuss the two-dimensional defects, which are the external surfaces. External surfaces are one of the most obvious boundaries in the crystal structure along which the crystal structure terminates. The surface atoms are not bonded to the greater number of the nearest neighbor, while the atom you can see in the interior of the crystal structure, they are bonded to the most nearest neighbor from the upper side and from the lower side, from left and from the right, while the atom at the surface where the crystal structure terminates, these surface atoms have the less number of the nearest neighbor. So as a result, these are therefore at higher energy states than the atom at the interior position. So the bonds of these surface atoms that are not satisfied to give rise the that is it, as a result it gives rise the surface energy, and this surface energy is expressed in unit of energy per unit area, that is joule per meter square. So to reduce this surface energy, material tend to minimize its surface. If at all possible, the total surface area, it tries to minimize its surface area. For example, liquid assumes the shape having a minimum area and the droplets becomes the spherical. But in the case of solid, of course, this is not possible with the solids which are mechanically rigid. Another crystal defects or interfacial defects is the grain boundary. So the most of the crystalline solids are composed of collection of many small grains like this ones. So such materials are termed as polycrystalline materials, that is composed of large number of grains. So this is the grain, this one is grain, this one, all these are different grains, and this one is the grain boundary, that is this wall which is separating the two grain, that is separating this grain from this grain. This will be called as or termed as grain boundary. So as the boundary is separating the two grains having different crystallographic orientations. So this one grain has its own crystallographic orientation, and this will be having its own crystallographic orientations. This is the unit cell directions of this grain, and this one is the unit cell direction of this grain. Both grain having its own crystallographic orientation. In broader view, we can see that like this one. This is the crystal 1 and this one is the crystal 2, and this one is the grain boundary, that is the, you can see that atom as the grain boundaries behave differently. It has its own different phenomena and which greatly influence the properties of the materials. So this is the crystal 1. Crystal 1 is having its own orientation, and this one is the crystal 2 which has its own different orientations, and these are the atoms at grain boundary which are separating both these crystals from each others. So we can say that the boundary separating the two grains having the different crystal orientations. The orientation on the polycrystalline materials, for many polycrystalline materials, we can say that the crystallographic orientations of these individual grains are totally random. So, under these circumstances, even though each grain may be anisotropic, this anisotropic means that its properties or each grain has its own directional properties, like bulk modulus, like its electrical conductivity will be different from each grain because each grain has its own crystallographic direction, and so these are the directional these properties which depends on the directions, so it will be different from each grain. So these properties like bulk modulus, electrical conductivities are different in the conductivities. These will be different in different directions, but as a whole specimen, which is the composed of grain aggregate, it will behave isotropically. Although the individual grains behave anisotropically, but the material as a whole specimen, which is the aggregate of all grain, this will behave isotropically. So, within the boundary regions, which is probably just a several atom distance wide, there is some atomic mismatch in transition from the crystalline orientation of one grain to that of the adjacent grain. So here you can see that these are in atomic mismatch in orientation. Both these grains have the different orientation. These are the adjacent grains. Because you can see that there is the various degrees of the crystallographic misalignments between these two adjacent grains. So when there is the angle of misalignment is large between the crystallographic orientation of these two grains, then this is called as high angle grain boundaries. And this one is the angle of misalignment, which is large for these two grains. On the other hand, we can say that this is the low angle grain boundary because here the misorientation or mismatch between the crystallographic orientation of both these grains is small. So this is called as low angle of misalignment, and this is the low angle grain boundaries. One thing more about this grain boundary is that the atoms which are along these boundaries, grain boundaries, are at higher energy as compared to the grain itself. So the energy of these grain boundary energy behave similarly just as the surface energy of the crystals. As we have already discussed, that the atoms which are at the surface of the crystal, where the crystal structure terminates, are at higher energy as compared to the interior of the crystal. This is just because that the interior of the crystals, the atoms have the more nearest neighbors and they have the more extensive type of the bondings as compared to the atoms which are at the boundaries. These have the less extensive bonding, so because of this, these are at higher energies as compared to the interior atom. So just is the case with these grains. These grain boundaries are at higher energies as compared to the interior of the crystal structures. So the energy of these grain boundary is the function of angle of misalignment. So we can say that for high angle grain boundaries are at higher energies because of greater misalignments between these two grains as compared to the low angle grain boundaries where the grain energy is lower as compared to the high angle grain boundaries. So here we need to discuss one thing more about these grain boundaries is that the atoms along these grain boundaries are the grain boundary in the polycrystalline materials are chemically more reactive as compared to the grain itself. This is just because of their grain energy. So the impurity atom preferentially segregates themselves along these grains because of their energy, because of the grain energy. So we can say that in the coarse grains where the area of the surface where the surface area where the grain area is large, where the atoms along the coarse grains have the lower grain energy as compared to the fine grains where the area of the grain boundary is small. So the grain boundary energy in the case of fine grain is higher as compared to the coarse grains. So we can say that from this discussion we can say that the grain boundaries in the polycrystalline materials are chemically more reactive as compared to the material itself, and these grain boundaries greatly influence the properties of the materials, and material engineers use these grain boundaries for the different purposes. It has its own different phenomena as compared to the grain itself. One simple small angle grain boundary is formed when there is the edge dislocations are aligned in this manner. This type of boundary is called as tilt boundary. So the tilt boundary between the two crystals that differs in orientation only a few degrees, consisting of series of edge dislocations. So you can see that here that these tilt boundaries are formed by the slipping of different planes. So because of the slipping of different planes, their edge dislocations are formed. Edge dislocations means that, as we have already discussed, that edge dislocation means where the plane of the crystal is terminated within the crystal structures, or when there is the half plane within the crystal structures. Such a type of defect is called as edge dislocation. So there are the series or the number of different types, number of edge dislocations which are arranged within this boundary. Such a type of boundaries are called as tilt boundaries, and these consist of series of edge dislocations. Twin boundary is formed, and this is the specific types of the grain boundary across which there is the specific mirror lattice symmetry. That is, the atom on one side of the boundary are located in mirror image positions of the atom on the other sides. So here you can see that in this figure, this is the grain 1 and this one is the grain 2, and the region between these two grain is called as twin, or termed as the twin boundaries. So the twinning is of two types. That is, there are the mechanical twins and there are the annealing twins. So the mechanical twins, which is result from the displacement that are produced from the applied mechanical shear forces. So such a type of twinning are called as mechanical twins. And on the other hand, when there is a deformations during annealing or heat treatments, so these deformations are because of these deformations, twinning occurs on definite crystallographic planes and in specific directions. So those twinnings which are formed due to the annealing or heat treatment of the materials are called as annealing twins. So both of which this depends on the either it is the annealing twins or mechanical twins, both of which depends on the crystal structures. Annealing twins are typically found in the materials which have the FCC crystal structures, while the mechanical twins are usually observed in the material which have the BCC, or BCC means body centered cubic, or HCP hexagonal or hexagonal close packed structures. So these are the two types of the twin boundaries which are usually found in different type of the materials, and these depends on the structure of the material. Thanks for watching. For more videos, please subscribe our channel.